Hello and welcome to this video. Today I will present one of our recent works to you. This work is called RapidChiplet, and it is a toolchain for rapid design space exploration of inter-chiplet interconnects. So let's start with the question, why do we even care about chiplets? As you might know, we are moving towards more and more advanced technologies to build chips. And if we keep using monolithic chips, where we have a single silicon die, then we encounter some challenges on the way. For example, we have low yield and high cost if we use advanced technologies. Especially we have high design costs, which makes it only economically viable to design a new chip if we have a large production volume. Furthermore, we are facing scaling limits of IOs, analog circuits, and SRAM. And last but not least, the slowest component on a chip often dictates its operation frequency. And one way to alleviate these challenges is 2.5D integration. Here, instead of having one big silicon die, we have multiple smaller chiplets that are integrated into a single packet. With this chiplet integration, we have higher yield and reduced cost, since a smaller chiplet has a higher yield than one big chip. Furthermore, we can use modularity and we can reuse chiplets. So for example, we can design a compute chiplet, which can then be used for different products. Furthermore, we can use heterogeneous chiplet integration. This means that in the same package, we can have chiplets that are built in more major technology nodes, for example, for IOs and analog circuits, and ones that are built in bleeding edge technology nodes, for example, compute chiplets. And finally, we can also use frequency and power binning when assembling these different chiplets into a couple of systems. So now you are hopefully convinced that chiplets are great. However, they also come with some challenges. And one of the biggest challenges is to provide a high throughput and low latency inter-chiplet interconnect to provide connectivity between chiplets. When designing such an interconnect, we have a really large design space, since there are a lot of different parameters. For example, the number of chiplets, the size of chiplets, but also the types of chiplets. We can, for example, have chiplets that contain memory or compute resources or IO drivers, and many more different types are possible. Then we can have different packaging technologies. For example, we can use an organic substrate or a glass substrate, or we can use a silicon interposer and so on. Furthermore, we can have different network topologies to connect these chiplets. For example, a 2D mesh would be possible, or a folded 2D torus, and so on. Furthermore, we can have different die-to-die link protocols, different routing algorithms for network traffic, different technologies that are used to build a chip, and so on. And in this design space, we often are facing tens of thousands of different possible combinations, and building all of these combinations to evaluate them or even simulating all of them is often pretty challenging. And furthermore, there are also a couple of different metrics that we are interested in. So we are interested in terms of the inter-chiplet interconnect for the throughput and the latency of this interconnect, but also for the silicon area, the power consumption, the manufacturing cost, and so on. And our solution to this challenge of exploring this large design space is a tool that we call RapidChiplet. RapidChiplet takes all of these different parameters as an input, and it provides fast and high-level proxies for our metrics of interest. And the aim of RapidChiplet is really to do this high-level design space exploration with tens of thousands of different design points. Once we did this exploration and we identified a couple of interesting designs, then we usually want to do some more accurate analysis on these selected designs. And to do this, we integrate the existing BookSim simulator. This is a flit-level simulator for network on chip. And there we get our more accurate simulation-based throughput and latency results. And just to give you an example for a use case of RapidChiplet, here in this case study, we wanted to explore the design space of the sparse Hamming graph network topology. This is a topology that is parameterizable And in this example, we had multiple tens of thousands of different design points that we wanted to evaluate. And for each of these design points, we wanted to estimate the latency that you see here on the x-axis, the throughput on the y-axis, and also the total area that is here indicated by a color. And here we were able to use RapidChiplet to see where these design points land in our plot. And we were able to plot different lines for Pareto frontiers under certain area constraints. So let's have a look at our latency and throughput proxies. Here again, we see a 2.5D stacked chip. And let's start with the throughput proxy. This proxy consists of 3 different parts. In the first step, we estimate the bandwidth of each link. If we have a look at a link, then this link is attached to a chiplet using C4 bumps or micro bumps. And the bumps of a chiplet are not all used for the same link. So for example, we look at this green link here, but instead they are used for a bunch of different things. So the bumps in the center here in red are usually used for the chiplet's power supply. And then the bumps on the beachfront are used for the different links. And since we only have a look at the green link right now, we can only take the bumps in this green area to build the green link. So to estimate the number of bumps available to this link, we take the area of the chiplet, multiply it by the fraction of the chiplet area that is reserved for the link, and we divide it by the squared bump pitch in order to estimate the number of wires of the link. To now get the bandwidth of the link, we have to subtract the number of non-data wires that are used for clock or handshake. In a second step, we estimate the total flow over this link. And to do this, we build the sum over all paths in our traffic. So here, say we have a known traffic pattern or we have a known trace of a target application. And what we do now is we build the sum over all flows in this traffic that use our green link that we are interested in. And we sum up the amount of traffic in that flow. To now estimate the overall throughput of our system, we take the minimum of the ratio between link bandwidth and flow over the link over the whole system. So we basically find the most congested link. And we multiply this ratio by the total amount of traffic. And this gives us a good proxy for the overall throughput in our system. At the first glance, this might seem a bit pessimistic, since we use the most congested link as a proxy for the whole system. But as we will see later in the evaluation, this is actually a pretty good approximation. Let's also have a look at the latency proxy. Here we only have a single formula where we estimate the average packet latency of our system. And we do this by building the weighted sum over all flows in our traffic. And for each such flow, for example, say this black dotted arrow here is one of these flows, we first take into account the latency of the source chiplet. This is the latency it takes to inject the packet into the network. And then we sum over all links in our path. So in the sum, in the first term of the sum, we would have this first link and also the intermediate chiplet. And in the second term of the sum, we would have the second link as well as the destination chiplet. And like this, we estimate the overall latency in our system. So these proxies are pretty high level. So they are expected to be less accurate than simulation-based results, but also let's compare them against simulations in BookSim. For our evaluation, let's start with the latency proxy. Here, we took a look at 4 different network topologies. We had the mesh, the torus, the folded torus, and the SID mesh. And we also considered 4 different traffic patterns. Here we had random uniform, transpose, permutation, and hotspot. And first, we have a look at the relative error. So here we assume that the simulation results are the correct results, and we see by how much our proxies deviate from it. And as you can see, for many traffic patterns, our average error is about 1%, or even lower. Only for permutation traffic, our error is a bit higher. But let's also have a look at the speedup. So here we see how much faster are we compared to flit level simulations in BookSim. And here you can see that the speedup is between 400 and over 1000. So we actually can save a lot of time in this design space exploration, while at least for most traffic types still being pretty accurate. Let's also have a look at the throughput proxy. Here again, we use the same topologies and the same traffic patterns. And compared to the latency proxy here, we have a significantly higher error. So the relative error for the throughput proxy is somewhere between 15 and 30%, which is significantly more, but it is still kind of okay-ish if we only do a very high-level approximation. The second part here is the speedup. And here we see that we have a tremendous speedup compared to flit-level simulations. So the speedup ranges from over 10,000 times to over 100,000 times, depending on the traffic. So as you can see, to do this high-level design space exploration where simulating all design points are not feasible, for these scenarios, our toolchain is actually very good. So let's come to the conclusion. We have seen that to design inter-chiplet interconnects for chiplet-based systems, we often have a very large design space with tens of thousands of different design points. And to evaluate a lot of different design points on a very high level, we introduced our RapidChiplet toolchain. We have seen that this toolchain provides throughput and latency proxies that estimate these metrics rather than simulating them. And we have also seen that we sacrifice a bit of accuracy in order to get a tremendous speedup. If you are interested in our tool and want to learn more, then we recommend having a look at our paper on arXiv or checking out our code on GitHub. And if you're interested in more news from our lab, then feel free to follow us on social media.